A beginner's guide to building a blockchain. Bitcoin and blockchain are among the most buzzwords these days. Even people who have never mined cryptocurrency or know how it works are talking about it. Hear the hype surrounding blockchain, which will now fix income inequality, keep all data safe forever, make everything more efficient and trustless, make the banking system redundant, save the planet. But what exactly is a blockchain? Can it really do all of these things? Can blockchain bring surprises to industries such as healthcare, finance, supply chain management, music copyrights, and more? In this article, I attempt to answer these questions by examining the implementation of blockchain in retail supply chain management and how it can bring greater transparency, traceability, and accountability. Retail supply chain management. We will study the following scenario where retail products, cotton shirts, jeans, and t-shirts, prepared by the manufacturer are transferred to the retailer via transport and wholesalers. We will use blockchain to track the movement of these products and the status of product delivery. In this way, when the product reaches the retailer, if there is any problem with the product, we can trace the source of the problem and set the responsibility. Let's start. What is blockchain? Technically, a block is an ordered set of transactions, while a blockchain is a linked list of blocks linked together by cryptographically generated hashes. You can think of a blockchain as the equivalent of a database with few other attributes. Consistency: incoming data cannot conflict with some other data already in the blockchain. Unchanged 3354 data can only be entered in append mode. Responsible: 3354 input data is locked to the owner and is replicable and usable. In the end, everyone agrees on the state of the blockchain. No one central party. Let's start with what these separate plates are. A block consists of a set of transactions that are unique across the blockchain. Each block consists of a set of features, as shown in the figure below. Timestamp: a previous hash of the transaction date, and time: a unique identifier that helps link the current block to previous blocks. If the previous hash is changed in any way, it will break the entire blockchain, because now the current block can no longer be linked with the previous block. Nonce: the current hash of the block is only generated if a set of predefined rules are met. Example: an approved hash would be one with at least 3 trailing zeros and a value of 55 somewhere in the hash string. To achieve this, miners, those who add blocks, go through multiple iterations. 1. Iteration: previous hash transaction index, nonce equals 1. Result: invalid 38 uxt 762 q80 7503 pog 0. Iteration 2, previous hash transaction index, nonce equals 2. Result: invalid 00 UITS 6209 BVGT 0943 q00. Iteration 3, previous hash transaction index, nonce equals 3. Result: valid 97 BHYT 55 KOU 345 ZLGVA 000. As we can see here, we received a valid hash after 3 iterations, and the nonce value also increases with each iteration. The nonce represents the number of iterations the miner went through to generate a currently valid hash. Once a valid hash is generated, the block will be added to the blockchain. Note: the iterative process of generating a valid hash is called mining. Once we get a valid hash that satisfies a predefined set of rules, it is called a proof of work. Current transactions: the set of transactions that occur in the supply chain, i.e. the movement of a product from manufacturer to shipping to wholesaler to retailer. Generated hash: the hash generated by the workload authentication. This unique identifier will become the previous hash of subsequent blocks in the blockchain. Index indicates the position of the current block in the entire blockchain. What are transactions in a block? Similar to blocks, each transaction on the blockchain is also defined by a set of characteristics. For example, the movement of cotton shirts from manufacturer to shipping will have the following characteristics. Below is an example of such a transaction. Timestamp 166,227,416.6 58973 /product ID /2 /product_serial number /50002001. Name /cotton shirt / source /manufacturer / destination / transportation / information / this product is in good condition / digital signature / approve / mark / and /. As we can see in this example, transactions get an immutable timestamp of when the transaction occurred. Product ID, name and serial number. The source and destination of the transaction, and the transaction message. Finally, a digital signature and flag value indicate that the transaction was approved for inclusion in a block. Note, a block can contain multiple such transactions. The current hash is generated by combining all these transactions in a block. Therefore, if an intruder tries to change any transaction in a block, it will cause a new hash to be generated for that block, breaking the blockchain. How to add a new block in the blockchain? So far, we've seen what a transaction is, how multiple transactions can be combined into a block, and how multiple blocks can be chained together to build a blockchain. But how do different entities, manufacturers, transporters, wholesalers, and retailers interact on the blockchain? How will blockchain help supply chain management? In fact, the blockchain structure will be replicated to all entities transacting on it, as shown in the diagram below. Therefore, when a new block is added to this blockchain, all entities must agree to add the new block to the blockchain by providing digital signatures. In the consensus protocol, all entities will contribute the resulting hash value, which is then combined with the transaction list, block index, and random value to generate a hash for the new block. Once a newly generated hash satisfies the specified set of rules, it is added to the blockchain and replicated for all entities simultaneously. Revisiting blockchain functionality. At the beginning of this article, we briefly introduced the key properties of blockchain, namely transparency, traceability, accountability, immutability, and decentralization mechanisms. Let us now see how these functions are performed in our supply chain management blockchain implementation. Transparency. Since a block can only be added to the blockchain, it brings complete transparency to all transactions if the parties involved come to a consensus. Traceability. If there is any fraudulent transaction or any intruder tries to change the state of any block, then it will result in a new hash being generated for that block. Therefore, this particular block will not be linked to its previous or subsequent blocks, breaking the entire blockchain. Therefore, we can easily find out any faulty blocks in the whole chain. Accountability system. Since each transaction in the block is marked with its source and destination, and its content has been verified by digital signature, we can set up an accountability system for this transaction during transmission, in case any problems arise. Immutability 3354. Once transactions are entered into blocks, and blocks are entered into the blockchain, they cannot be changed. You can only enter data in append-only mode. As we have already described in traceability, changing a block or transaction will cause the block to fail. Finally, there is no central party that governs the entire blockchain. Instead, parties must build consensus, which leads to a decentralized power mechanism. In summary, we talked about the following points. What are blockchain transactions and their main characteristics? How to combine transactions into a block. How are blocks added to the blockchain according to the consensus protocol? How can blockchain bring transparency, traceability, and accountability to supply chain management? The applications of blockchain are limitless, and we are just getting started.